Hello, my name is Edward, and today I'd like to talk to you about blame trees. Suppose that you were working on your WADS 2013 submission. You, being a collaborative person, have a number of co-authors, and you'd like to work on your paper at the same time as everyone else. Now, of course, when people are editing the same paper concurrently, you may end up with different versions of the document, which have different changes. Someone might change the title, while someone else might change the abstract. And what you'd like to do is you'd like to merge these changes back together. Document merge is a very important problem. It occurs in a variety of contexts, especially in source code control systems. And as such, there are a number of tools available to help you do it. So you might wonder, well, is document merge a solved problem? Well, let's take a look. We'll look at one specific merge, Git's three-way recursive merge, which proceeds as follows. Suppose I have two documents, document 1 and document 2, which I'd like to merge. Document 1 has the contents A, B, while document 2 has the contents C, A, D. The first thing we need to do when attempting to merge these documents is take their histories and look for a common ancestor. This ancestor will play a critical role in the resulting merge. That's why it's called a three-way merge. There are three documents involved. Next, we'll take the longest common subsequence. We'll calculate the longest common subsequence between the ancestor and the documents. Longest common subsequence is a non-contiguous sequence which occurs in both documents, and the longest common subsequence is the longest such one. So in the example of the first document, when we compare the ancestor, we see that A is contained in both documents. Since that is all that is in the ancestor document, it is by definition the longest common subsequence. And we can take this and align B so that it comes after the A in the first document. Similarly, with document 2, we once again align A with A and see that C comes before A and D comes afterwards. To perform the merge, we simply walk down the ancestor document, looking at the aligned versions of the other two documents and inserting or deleting elements as necessary. So when we look at the space between the beginning of the document and the letter A, we see that document 2 has inserted a C, so we record that in the document. Then we record down A, and finally between A and the end of the document, we see document 1 has recorded B, while document 2 has recorded D. That's a conflict, so we'll write that down and also ask the user to resolve this problem. There's one thing that I haven't mentioned, which is why it's called a recursive merge. Now, in Git, the model of documents is that of confluent persistence. That is to say, a document can be reused and merged back together arbitrarily many times. When you have a complicated history graph, there may be multiple ancestors, which are most recent in some sense, and it's not clear which one merge should pick. In a case like that, what we should do is we should merge the ancestors together, and the resulting result of the merge should be used to actually perform the original merge with the two documents. This is why it's called a recursive merge. There's a recursive call to the merge function. Confluent persistence is what makes merge algorithms hard. Otherwise, we could make a number of simplifying assumptions about our environment. To sum up, Git's three-way recursive merge requires O and K time, where K is the number of recursive calls. Usually K equals 1, but if we have to do many recursive calls, it could be higher. It also requires us to know what the entire history of the document is. We have to find the ancestor, after all. So, this is not too bad in practice, and if you've ever merged a document, this usually does not cause you too much trouble, but there are a few things that are not so good. For example, it's not asymptotically optimal. If the documents are exactly the same, we'd imagine that we'd like our merge algorithm to discover this more quickly. We don't want to have to scan over the entire document just to decide that there's no work to do. And when the document is large, that can be a big problem. Both performing the merge which requires a linear scan over the entire document, as well as maintaining the history of the document, can be quite expensive. Finally, three-way recursive merge built out of the longest common subsequence can be inflexible. Longest common subsequence dictates the only possible way the merge can be carried out. There's no way for the user to say, "Oh no, I'd like my documents to be aligned differently." They may know that because when they performed an edit, there's some semantic knowledge about how the diff worked. So, what are we trying to do here? Well, blame trees what we would like to do with blame trees is we'd like to make the time better. In a three-way recursive merge, it takes linear time in the document. We'd like to only spend time on the conflicting regions of the document. For the shared regions, we'd only like to spend time logarithmic to the size of each shared region. We'll achieve this using a structured document representation, rather than the flat text model that Git's merge algorithm assumes. So let's talk about how we have to change our document representation to support blame trees. We have a sequence of characters, which is the model of traditional version control system merge, and now we are going to convert it into a sorted associative map. Sorted associative map has keys and values. The keys can correspond roughly to line numbers. Now, they're not really line numbers because the third line of a document does not have to be stored at key 3. Instead, they just have the property that if I have two line pseudo-numbers, I can take them and produce a new line number, which is between them. This kind of data structure is well known, and we know how to do it in constant time. The values of our associative map will correspond to fragments of the document that we would like to merge. This granularity is a parameter that the user can choose. They could, for example, decide that they want to do their fragments by word or by larger sections. So we have taken a text document and converted it into effectively a binary tree. And we can use this as a functional data structure, which automatically gives us confluent persistence. Our result has to do with how these trees can be merged together. In particular, we can merge two trees together in time equal to the time it takes to do conflict resolution on the non-shared nodes, plus the sum of each of the logarithm of the size of each shared region. That's a lot to take in, so let's unpack that. Shared regions are portions of the original document which have the same keys and values. They may not correspond directly to shared subtrees because a shared region may be spread out over multiple nodes of the document. So a shared subtree is identical between the two representations, whereas a shared region simply shares the same keys and values, but may be structurally different. All of the other nodes, which are not shared subtrees, are the non-shared subtrees. We are going to have to merge these together because they correspond to conflicting regions of the document. For example, we parameterize our algorithm by a conflict resolution function R. This function will take two segment regions of the tree. For example, here we have the very first segment of the tree, which does not have any corresponding section on the other tree, and we're going to merge this together using the R function. We're going to resolve the conflict. We can also take these two nodes, which, while part of the shared region, are not identical nodes and need to be merged together as well, though we can optimize this call away. And finally, this last region at the end of the document, which also needs its conflict resolved. In general, we expect conflict resolution to take at least time linear to the number of nodes that are conflicting. After all, you have to look through the nodes to figure out what has gone wrong. So we've explained what it means for us to get this time bound, and if there aren't many conflicts, then this should be a substantial improvement over the linear time algorithm that the original merge algorithm required. But how are we going to achieve this? The key idea is that we are going to annotate all of the subtrees with their last update revision, so-called blame. Blame is a very simple concept. The idea is that if you have some document and you have some line, you'd like to know who was the last person to edit that line. Git provides this functionality as a command, git blame, and here is some example output from that command. On the right-hand side, truncated, but the content's not important, is the content of the document that you were blaming. And on the left-hand side is the revision annotation for each line, which says when the content was updated. Git also inserts a number of extra information, which simply could be derived from the revision itself. Now, Git has to compute this information every time you ask it for a blame by walking backwards in the history. But we're going to do something different. Let's record the blame in our data structure. So coming back to our tree, we simply add a new field, the revision, which says when each node was last updated. To update the revisions, we simply use the same path copying trick that is used for normal binary tree update, replacing each of the revisions on any node on the path with a new node. The key invariant with revisions is that if the keys of two subtrees are the same, and the revisions are also the same, then they must correspond to the same tree, and vice versa. So now our algorithm can proceed as follows. First, we traverse our trees, identifying shared regions between them. Then we split the tree between the region boundaries. We'll now have a list of subtrees which alternate between shared and unshared. For each of the unshared regions, we zip them up and perform conflict resolution on them to result in a single tree. This gives us a single list of trees, which we can now merge back together. Now, we know how to split and merge red-black trees. It takes time equal to the sum of the logarithms of the size of the trees we're splitting into. So there's no problem there. Additionally, we've made the conflict resolution a parameter of our algorithm, so we also know how to do that. So the only question is, well, how do we identify shared regions of the tree? Our first solution is so simple that it is really simple. Suppose that the trees have the same structure. Then all we need to do is walk the trees, and when we see a pair of subtrees which are shared, we can bail out. We immediately get the bound that we wanted. But there's a problem, which is it requires the trees to have the same structure. If any of these keys were renamed, or the trees were not exactly the same shape, this method is no good. When the trees are not the same shape, we have to still manage to visit the keys in the right order. We can do this by performing an in-order traversal, where the left subtree is visited before we do any operations on the node, and then we visit the right subtree. Now, if we just do in-order traversal, we'll end up walking every node in the document, which is no good. It's linear, just like the original algorithm. So we need to short-circuit the in-order traversal. Here, first, the traversal proceeds as normal until we encounter a node where the revisions and the keys are the same. In this case, the key is 2. Now we know that the trees are the same, so we no longer need to visit the right node. We march up the shared subtree until we reach the last node which is shared, and we continue our traversal from there. This allows us to skip traversing the entire subtree. We only need to go down to the bottom left leaf in order to discover that we are in a shared subtree. Now, unfortunately, this algorithm gives us time log square in the size of a region. Why is it a log square? Well, the problem is that a shared subtree is not the same thing as a shared subregion. If I have a shared subregion in a document, it may be translated into multiple shared subtrees in my tree representation. Now, there are only logarithmically many of these trees, but when I do my traversal in this fashion, I have to march down to the bottom left of each of these shared subtrees. This adds an extra log factor and results in the square in the term. Thus, we'll have to do something more clever. So our third solution utilizes level order traversal. It requires a stronger invariant on the trees, namely that they are perfectly balanced. Now, as it turns out, this will be fine in practice. Level order traversal will start by maintaining a queue for both trees, and this queue will be initialized with the with the root of the tree. We look at the leftmost key of the tree, and we use this to decide which tree we're going to walk. For the left tree, in this example, the left tree has the key 1, so we can start traversing it immediately. To traverse a node, we check if it's the same, if it's a shared tree, that is to say, if it is identical to the head of the queue of the other tree. In this case, they're not the same, so we'll have to split the children and add them to the queue. So we now have the subtree containing 1, 2 in the queue, and the subtree containing 3, 4 in the queue. And now this tree is done. We now have to operate the right-hand side tree, and as we can see, it doesn't match up with anything, so we also split it up. Now that both trees have finished their traversal, we now begin again. Once again, these trees do not match, and so the left tree proceeds first by inserting 1 and 2 into the queue. But now notice that the right-hand tree has the lower leftmost key, so now it proceeds. Now once again, there's no match, so 2 and 3 are added to the queue, and this proceeds as you would expect. Finally, we get on the level where there exist shared subtrees. As before, 1 does not have any match, so it has to be decomposed into its children. But now, when I look at 2, I see that 2 is a shared subtree in the other tree. So I can immediately remove it from the queue without adding its children. The same goes for 3 and for 4. 5, of course, does not have a shared subtree in the other tree. And in fact, we know that there are no longer any possible shared subtrees. So we can abort at this point as an optimization. This scheme achieves our logarithmic bound in the size of the shared regions, and the reason is because we only ever traverse unshared nodes, which we can charge to the cost resolution function. To conclude, level order traversal works for red-black trees, where the invariant is that there are a constant number of black nodes in each path. So whenever a red node is encountered, we simply immediately add its children to the queue. We do not bother checking if it's shared. This bound matches the optimal bound set by adaptive merging algorithms, which have a similar pattern. If you are doing a sort, you may expect that if your list is already sorted, you do not need to take n log n time. This O of the sum of the logs of the regions is a common pattern for these algorithms. Now, unfortunately, there are pesky constant factors which make this algorithm a little less than practical for use at the moment. We have to encode the size of the tree as well as all of the extra fields, including the revisions. So we might expect this would only be useful for large documents where this overhead is negligible. And there we have it. Blame trees, a way of performing fast merges on documents without requiring history and without requiring the history of documents by encoding information about who last revised any given node in the document. Thank you very much.